Welcome. I'm going to talk about acceleration. Acceleration in this video. Now, we all know what is acceleration. If you run faster and faster, or if you go faster and faster in a car, you're accelerating. So let me sketch an example. So for example, if I have I'll just talk about a ball. Alright, so it's a ball which is rolling along the ground or sliding, if it's a very smooth ground. Now suppose that it starts off, well, give it a push, and it starts off with a speed of say 1 meter per second, right? And it's going to the right. So and suppose that after 1 second, now ball is not going to go faster and faster on its own. So no, actually let me change to another example. Let me change to a car. Let me just change to a car. That is well, that's a bit complicated to draw. I'm going to just use a box to represent a car. So let's say that's my car, right? It looks like a box. So it's let's say at a certain time when I looked at it, it's the driver is going at 1 meter per second, and let's say after 1 second, the speed increases. The speed increases to 3 meters per second. 3 meters per second, and after another second, it increases to 5 meters per second, and so on. Okay, so clearly it is accelerating. It's going faster and faster. So we call that an acceleration, and that's what we normally say when you see a car going faster and faster. Right. Now let's develop this idea of acceleration in physics a little bit more. You'll see in a bit that we start getting things that looks quite different from what we expect in everyday life if we develop the idea logically. So for now, let me just ask the question. Simple question: how fast is it accelerating? Well, in physics, we need numbers, we need quantities to specify exactly how fast or how much or how heavy or how long. So how fast is it accelerating? How would we answer such a question? This is how we would answer it. And like I say, the acceleration is really about how it's getting faster and faster. So how are we going to describe this? So it's not just about how fast, because how fast is just the speed, but the speed is going faster, getting faster and faster. So the way to describe or specify acceleration in physics is to say how much the velocity has, or the speed has increased. How much in this example the speed has increased in a unit time. Alright, so before going into this abstraction, let me just write down what the acceleration would be according to this description. It would be, as you can see, it increased from 1 to 3 meters per second. So that's an increase. That's an increase of 2 meters per second, right? An increase. So 2 meters per second is added to the 1 meter per second, so it becomes 3 meters per second. That happened in 1 second. So we say that the acceleration is 2 meters per second in 1 second. Okay. Okay. Let me first write this down first. I can say that the acceleration is 2 meters per second in 1 second. So that's exactly how I can describe this in physics, and that's a very clear and specific number and description. I know exactly how much it increases in 1 second, and that tells me the acceleration. And after another second, as you can see, when it increased from 3 to 5, it has clearly increased by another 2 meters per second. Okay, so in this example, in this example where the speed increases by the same amount every second, we call this a uniform acceleration. And we are going to see the word acceleration. We are going to see the word uniform used quite often in this topic on velocities and acceleration, and the word uniform just means same. So it's the same acceleration in the first second, the same acceleration in the next second, and so on. So if the acceleration stays the same, we describe this using the word uniform. It's just like when we wear uniforms in school, we all look the same. So that's exactly what uniform means here. Not our school uniform, I mean in the sense that you have the same acceleration from second to second. So that's how we could write this, 2 meters per second. Now let me develop this idea from here to make it a little bit more general or abstract, as you might call it. So I'll start with the symbol. So 2 meters per second in 1 second. Okay, we might call this 2 meters per second. 2 meters per second, that means just the same thing. Okay, as you can see, I'm developing the units to make it more and more like what we normally use in physics. So per second, right? Now, when's the last time we see this per second thing? That's when we talk about speed or velocity, right? Speed. So for example, if I say that the speed is say 3 meters per second, that's how I would read this in English, 3 meters per second, and it is this part here, the over stroke second, which means divide by second. All right, and it's this part which is what the per second really means. So that means that per second means the same thing as this stroke, this over second, or this divide by second. So by extension, I can write per second using the symbol over second. And you don't see this very much in textbooks today, but it used to be fairly common in older textbooks when I was little. Right, so let's press on. Now, that is a really cumbersome way, which is why maybe why it's not used so much today. But let me look at this meters per second per second. Well, what does this mean, meters per second per second? It means you can think of this in a number of ways. It can mean meter divide by second and divide by second again. Now there are a few ways we can write this if we think of the m, s, and s as variables in algebra. Okay, so what it just means is that I can say, for example, m stroke s is like m over s. Okay, and I divide by second again. Okay, and that can mean, for example, that can mean m over s times 1 over s. Okay, m over s times 1 over s. Now, if I multiply the s and s, I get s squared. Right, I get s squared. I get m over s squared. So I can actually write this as m stroke s squared, and it just means the same thing. Or alternatively, in a form that is commonly used today, we could write this over s squared as m times s to the power of minus 2. So you'll see this quite often in questions these days. In fact, maybe even a bit more often than this. So there we have our unit for acceleration, meters. I normally call it meters per second squared, but you can call it anything you like as long as you understand what it means. So let's press on to make a definition for acceleration. In physics, we need definitions to make the meaning very clear, and so that we know exactly how to use and calculate the term for all situations. So how would we make a definition of this? Now, the first thing, even before we make the definition, I should go back to the way I described this I've been describing this as an increase in speed. Now, I now need to make that more specific, right? It should be the change in velocity that I'm more interested in. Acceleration is normally defined in terms of it's well not well it's always defined in physics in terms of velocity and not just speed. Okay, and the subtlety, that's the difference. The difference at this point is a little bit tricky to understand, but I'll explain a bit more later. So let me just say that we need to think about acceleration as a change in velocity, and with this let me write out a definition for this. Okay, I should clear this up. And let me call this, let me just write this out as 2 meters per second squared. I'm quite used to the stroke, so I just leave it at that. Now, okay, so let me write down the definition. Definition of acceleration. Now, the definition of acceleration goes like this. It is acceleration is the rate of change of velocity. Okay, so that's, if you remember how I described the word rate in the earlier video on velocity, it just means the change per unit time. Okay, but I also mentioned how it is how the rate also carry the idea of at a particular instant in time. That means that how fast it's changing at any particular time. But I'll talk a bit more about that later when I talk about instantaneous acceleration. So for now, you can think of this as one version of the definition, which is a little bit abstract because we use the word rate, which means, okay, let me just say the change per unit time. Okay, now if you have a change and it happens over a certain time, and we want to find what is the change per unit time, the way to do it is simply to divide that change by the time taken. So just like we did for velocity. So let me write out this other version for acceleration. Acceleration is the change of velocity. Change of velocity over I need a calculation. It's the change of velocity divided by the time. No, that's the formula. Okay, let me try again. Acceleration is a change of velocity per unit time. So, and this is in a form where we can more easily make a formula. So let me make the formula for that now. Okay, let me just say that, let me go back to my previous example. Now I'm going to look through this again and think about how to calculate this, but I'm going to modify the example a little bit. Okay, I'm going to change those times, and I'm going to change this. Okay. Okay, I'm going to say, right, let's say the time from there to there, where the velocity increases by 2 meters per second. Let's say that the time taken is 4 seconds. It takes 4 seconds to go from here to here. another 4 seconds for it to increase by another 2 meters per second. So now let me just say that I don't actually know that it is increased by 2 meters per second. I have to work that out. So how would I work that out? Right, I would take say in this first 4 seconds, I would take the final velocity, and I would minus the initial velocity. So that gives me the 2. That gives me the change of velocity. So I would take 3 minus 1 to get the 2, and then but I want to find it for per unit time. That means in this case for seconds is my unit. So for 1 second, and since there are 4 seconds, I would need to divide by 4 to get the change in 1 second. So there we are, and all we need is to calculate this, either whether by hand or with a calculator, and that gives us 1/2 meters per second squared, and that's our answer for this case, for this example. Okay, so far so good. Now, but I did say I wanted to make a formula for this, I think. So how are we going to have a formula, right? You know formulas, you need variables, and you need algebra. So we need some letters to represent each of these quantities. So time is easy. We often use T to represent time. Now I need a formula for final and initial velocity. The final velocity is often called V, and the initial velocity is often called U. Okay, V, U, and T. Now I have my letters. So these are the 3 letters, and if I come here, the 1 here is the U, right? The 3 here is the V, and the 4 here is the T. So all I need to make my formula, I call my acceleration A, is to just replace these numbers by the letters. So let me write this out here. So A, the acceleration, is equal to V minus U over T. V minus U over T, and there we have our formula for acceleration. So you're going to see this quite a bit if you're doing a course of physics, and that's our formula for acceleration. Okay, now so far so good. Now I'm going to do something. To sort of mess things up a bit. I'm going to look at some other examples, mainly to see how we can bring in the full meaning of velocity. You know what velocity means. Velocity is not speed. Velocity also means direction. But so far I've just been giving numbers to the velocity, and I've not even mentioned a single word of direction. So how does that come in? Well, that comes in when we use this formula, and that really messes things up and cause a lot of confusion if you're not careful. So let me start with some examples. Right. I'm going to clear the whole lot. Okay, I'm going to start over. Now let's say I have this example. Where I have a car. Again, my little box means a car, and suppose that this car is going in this direction with a speed of 5 meters per second, and suppose that after 2 seconds, the speed decreases to okay, let's say 3 meters per second. So what is the acceleration? Right, so that's my final, that's my initial, that's the 2 seconds. So I can calculate that. I know the formula. I derived it. So V is the 3, U is the 2, is the 5, and t is a 2. Okay, then I do the calculation and I'll find minus 1 meters per second squared. Now we start seeing something unusual. We see a minus sign down there. Now what does the minus sign mean? Now the minus sign, many students would think that the minus sign means that it is slowing down, and indeed in this case, in this example, it is. So minus, let me write this down, a minus sign means a deceleration. Deceleration, often we normally think that it means slowing down. Okay, that's what people, let me emphasize this point. That's what students often, that's what many students often think, at least many students that I know. Now I'm going to underline the word think. Now I hope you see where I'm going. Okay, I'm going to prove that this is not quite true. This is not quite true. A minus sign does not have to mean that it is slowing down. Now why does a minus sign not have to mean it is slowing down? Okay, that's a tricky bit here. Now the reason is this. There is a step which is missing in this whole calculation. Alright, and what is the missing step? Now the missing step is that velocity is the meaning of the velocity. Velocity is a vector, and velocity has direction. The missing step is that we have not actually included the direction in this calculation. We have not actually considered the direction in this calculation, and something is missing. Alright, something must be missing. So what is missing? What is missing here is that we have to think of a way to include the direction. And the way to include the direction is often quite complicated for motions in generally on a road or in the air, when you throw a stone and all those kind of usual things that we do every day. But in this case, when we have motion along a straight line, the way to do it is to say, right, we are going to choose either one direction along the straight line as the positive direction. So you can either choose this or this as the positive direction. Now usually for some reason many people would naturally choose the right side to be positive and left side to be negative, but I can equally well choose the left side to be negative. Okay, so if I do that, then what I need to do, even before substituting these numbers, there's something else that I need to do first. I need to include the direction in my v and the u. So my v and the u, how would I include the direction? Right, for this simple example, the way to include the direction is by adding the signs, putting the signs in front of the number. So instead of just saying that u is 3 meters per second, I should say that it is plus 3 meters per second, and the plus means that it is going in the positive direction, which in this case is to the right. Now what about the that was actually 5 for the initial velocity, so it's plus 5 meters per second, and v, final velocity, is 3 meters per second, and we use the plus sign to indicate that it is to the right, to this direction that we call positive. So now that we have the signs, if we do the calculation again, we should remember that this is a positive number, plus 3 minus plus 5, and we get minus 1. We get minus 1. Now, according to this logic, this rule, if I have a minus sign, it means that it is to the left. So what I actually have here is an acceleration of 1 meters per second squared to the left. But what does that mean? The car is obviously moving to the right. What do you mean by an acceleration to the left? Right, if the car is moving to the right, then an acceleration in the opposite direction just means that it is slowing down. So that's how we can, that's a much better way, much more systematic way to treat and understand the signs. So we have this situation now. Okay, if we have this result now, if acceleration is opposite to velocity, the body is slowing down, or you can say decelerating. I prefer to use simpler words.